Hey guys, my name is Anya, and I'll be going over my discrete structures final phase one, problem one on weak induction. Let's just hop right into it. It's a cool explanation. So the problem we are assessing today is proving using induction that 9 to the nth power minus 1 is divisible by 8 for all n greater than 0. So we want to begin with our base case for this problem. We will be arguing by induction, of course. And so we find that n must be greater than 0 as stated in our formula. So n is greater than or equal to 1. Now we can plug in our first n value of 1 to just prove that 9 to the n power minus 1 is divisible by 8 for a value of n. So once we plug in 1, we use a formula, 9 to the n power minus 1 is equal to 8t for some integer t. And of course we get that 8 is equal to 8t, which is true. Because this statement holds true, we now have a formula 9 to the n minus 1 is equal to 8t for any integer t. We now can see that since the formula holds true for n, then we can find out if it holds true for k. This is our inductive hypothesis. And we then substitute k for n, and when substituting in k for n, we also find that k is any value greater than 0, similar to n. This is our p of k formula. Our formula now reads 9 to the k power minus 1 is equal to 8t for some integer t. Now we want to move on to our inductive step. This proves that if our statement holds true for any given case where n is equal to k, then it must hold true for the next case where n is equal to k plus 1. This will hold for every natural number n if this proves true. So for any k greater than 0, if p of k holds true, then so must p of k plus 1. So just a quick recap so far on what we established. We established our base case where n is greater than or equal to 1. And then once we plugged it in, we found that solution, when we plugged in 1 for n, is in fact divisible by 8, making the statement true. Then we found our inductive step, proving that since the statement holds true for n equals k, then it must be true for the next step, n equals k plus 1, which we're currently trying to prove for. Which leads us to our inductive hypothesis, which we're trying to prove for, which we stated once we plugged in at k for n, that our inductive hypothesis, which is now 9 to the k minus 1 is equal to 8t for some integer t, is possible to be divisible by 8. Now we want to begin proving our inductive step for p of k plus 1 and p of k both being divisible by 8. To do so, we want to take p of k plus 1, which is also written in formula form as 9 to the k plus 1 minus 1, equaling 8m, m being any integer. I don't want to use similar variables in this case. And p of k equaling 9 to the k minus 1 equals 8t for any integer t. And I want to prove this induction step. So in this inductive step, it's a lot of algebra, so I'm going to try to break it down as fast as I can, or as much as I can, I'm sorry. So to begin by taking our 9 to the k plus 1 minus 1 and rewriting it as 9 multiplied by 9 to the k minus 1 plus 8. If you know any exponent rules, 9 to the k plus 1 is just base 9 multiplied by base 9 raised to the k power. The plus 1 is the same base, which is 9 raised to the 1 power is where the 1 comes from. And if you were to do out or distribute the 9, we'd get a negative 9. That's where the plus 8 comes in, completing our formula for 9 to the k plus 1 minus 1, now being rewritten as 9 multiplied by 9 to the k minus 1 plus 8. And just as we had mentioned before in our original inductive hypothesis, 9 to the k minus 1 is equal to 8t. So now we can substitute in 8t for 9 to the k minus 1. So now we have 9 multiplied by 8t plus 8, which can be rewritten in terms of 8, which gives us 8 multiplied by 9t plus 1. And of course, because it's in terms of 8 and 8 is also in parentheses, this does in fact prove that 9 to the k plus 1 minus 1 is divisible by 8. Our final formula of 8 multiplied by 9t plus 1 is in fact divisible by 8. So this proves our inductive hypothesis, saying that 9 to the k plus 1 minus 1 is in fact divisible by 8. Thank you guys for listening, and this has been Anya.